Welcome back to the second part. In this video, I'll be talking about the derivative of r, the range, and h, the maximum height. Now, let's just start with range. Range is always, as in distance, it is the distance, the displacement by the cannonball from either side of the parabola, from here to here. This displacement is the r. Now r is just like the component in speed time 1, where s is equal to the distance divided by the time taken, where speed is the distance traveled per unit time. So yeah, it is d by t. Just like that, r is the distance or displacement. Vx times t will be a formula as in distance is equal to speed times t. Vx will be our horizontal force or horizontal velocity component, velocity x. So as in to indicate the x side or the horizontal side, and the time taken, which is just t. So t, which we derived in our previous video, was 2v sine theta divided by g. So now we know that the range is equal to Vx times t. So Vx is just V cos theta. So we know cos is equal to is adjacent by hypotenuse. So now taking that, h will be our velocity or the vertical or the velocity that is 20 meters per second, which will give our horizontal velocity, which is Vx, the adjacent one. So with that, now let's just substitute the values. R equals V cos theta times 2V cos, sine theta divided by G. Now, we can simply simplify the trigonometric identity twice the theta, which is just 2 sine theta cos theta will now be our 2 sine 2 theta, and that's how we get our range formula as r is equal to v square times sine 2 theta divided by g. Now this will be a formula to find the range in meters, that is the displacement of the cannonball. Now the maximum height h. So this point is reached when the range is halved. That will be our tip of our parabola or our inverted parabola. So we just half the value, we half the range. Or what we can do is we'll start it from the first. So as in the as but the thing is we have to take into account the vertical velocity component, which is Vy. I define it by Vy, and Vy is just V, the velocity provided by the cannon, times the angle in relation to the ground. So yeah, that is our vertical velocity component. Now, taking into account that the maximum height is reached when the half of the time is being there, or half of the range. Now, we can't actually say half of the range because it's lesser accurate when we say it as half of the entire total flight time. So in this case, I'm just going to say it as half of the total time. I'm not using half of the range because that's not pretty accurate. So we'll just go with half of the total flight time. So half. So the time formula still stays the same in here. So that's v sine theta divided by g. Now times the vertical, the vertical component, which is v sine theta. Now you see that? So that's going to be half of v square times sine theta the whole square divided by g, and that will be our H formula. And that's how we get the formulas for the range and the height. Now also in today's video, we'll be also looking at a projectile motion which got no angles to deal with. As discussed in the earlier introduction of projectile motion in my previous video, we use a formula called SUVAT. The SUVAT is a classical formula to find the displacement when the acceleration is constant. Now we'll use the classical formula, which is S equals ut plus half at squared. Ut will be our initial velocity, and t, which is just 0, so this mostly remains as 0, and half of a, the final velocity, and the time taken at the end squared, just the time. Okay, and s will be our displacement. And remember that this only applies when the acceleration throughout the entire process is constant. Now, let's take an example of a cannonball, the same cannonball being pushed off a cliff at 10 meters per second. Now, this also is the gravitational force. So, it doesn't much deal with the gravitational force. So, I'll just take it as the ball is being pushed at 10 meters per second. Now, we all know that the acceleration due to gravity is constant at the Earth's surface. So this 10 meters per second will be always be constant. Remember that I'm not taking the g value as 9.8, I'm just taking it as 10 for simplicity, so that we don't get a time as in decimal. So I just wanted to say that. So we are actually taking time, we're taking the gravitational force as 10 meters per second, and the ball is being elevated from the ground level by 20 meters. Now we have to find the range or the displacement where this ball will fall. This is half of the parabola, where now this will be our maximum height. This will be our maximum height. So this is the only part that it's going through, this part. So now we'll just apply the SUVAT equation, which is S equals ut plus half at squared. So we know that the displacement is minus 20, since the ball is being fallen off a cliff where this is 20 and as it's descending, it should be minus 20. So with the displacement being minus 20, and as I said, as the ball is in rest, which is just 0 minus half of the gravitational force, or the A, which is 10 meters per second, or I'll just leave it as such, and the total time taken. So we don't know the time, so that's what we are going to find out first, and then we'll find out what we have and we'll find the range somehow. So t is equal to the square root of 2 times 20 divided by 10 by putting all of the other stuff into this side and taking the squared as a square root. We get the time as 2 seconds. So remember how we found out the range. Range is the horizontal velocity component, or Vx, times the time. So we know that the time is 2 seconds, and we know the horizontal force acting on it, which is the gravitational force, is 10 meters. So total range will be 20 meters. Thank you.